One more person is supposed to join, but I don't know. Let's start. Yes. No, not yet. We will just be continuing the counting thing that you were doing yesterday. So we will start with the counting problems left from yesterday. Okay, that I had given. So let's finish them off. Okay. So problems left from yesterday, and then we will see more variations and things like that today. Okay, problems. A problem left. Just one problem first left from yesterday. Or let me just start with a very simple question, a simple problem. Okay, simple path counting problem. Let me start with this. This is a simpler one. I think it's good to do this first. So this is again with the diagonal moves. So we'll just say diagonal moves. But so last time we did this, we wanted to go from the origin to somewhere like, let's say 10 comma 0, right? And we figured out how to do this with diagonal moves. Now diagonal moves is understood, right? Northeast and southeast. But today, let's say if I change this and let's say if I ask the question, number of paths from, maybe I'll just write the question first, then I'll draw my thing. So number of paths from 0 comma 0 to let's say 7 comma, let's say 7 comma 9, yeah, with diagonal moves with northeast and southeast moves. Okay, so with these two moves we would like to understand. So let's think about this. It's just a simple variant. So so we want to get somewhere here, right, to 7 comma 9. Now we're not going to explicitly draw and everything now. Okay, we'll do this faster. So let's say we want to get to 7 comma 9. So how many ways would be there? I suppose these are not even useful, because if you want to get here, you would not be using these. So yesterday it was like 8 comma 0, 10 comma 0, but now we want to go somewhere in the middle or somewhere. So if it was like 8 comma 0, then it would be equal number of northeast and southeast moves, right? what would you, so basically if you want to figure out how many northeast and southeast moves will be needed, something like that, right? How many of each can that be said? And if it can be, then how many, what is the exact number? Okay. How many of each move? So this is very similar to what we have been doing to the easiest variations that we had. Knowing how many of which move is needed. Like if there was 3 kinds of moves, then it is difficult because then that's not possible to determine. But here it should not be difficult. So just try to ask yourself how many northeast moves and how many southeast moves do I need to reach 7,9. You can go below also, remember, okay? You are allowed to go below also. Just an example, you can take, wait, hold on. Okay, let's think about this. Yeah. Is it even possible? Anyone, is it even possible that you reach 7,9? That's not very difficult, right? To just think, if I, how would I like find one way to reach or try reaching there and see? It seems like it is not possible. Or even if you just take the up steps, 6, 7, 8. This is 8. This becomes 8. Anyways, I'll make it 8, not a problem. I think it is still not possible. Something like that. Or there is no such thing here. 9,9 or 8,8 or 7,7, something like that, right? Yeah, 7,8 or yeah. I mean, so this is something is wrong, but you can understand, right? If you keep going northeast, then by the time you make 8 moves, you will be reaching 8,8. So what is wrong in the diagram? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, this is just 8. So 8,9 would be to the right. So you can understand. Yes, it is not possible. Simply speaking, it is not possible. But you would think that, okay, I mean, I got it, that's fine. You got it, it's fine, but it's very simple actually. I mean, it's clearly not possible. I mean, if, sorry, no, this was correct, right? Why am I changing this? This was correct. This is 8 comma 9. Yeah, it's one step above and you cannot reach there simply. Yeah, this is 9 comma 9. Yeah, so it is not possible with these moves. It is as simple as that. Okay, so just by logic it's very clear, but in general, how would you make such decisions? I mean, how would you develop a machinery to make such decisions? Or how would you, set up some variables? So let's take the help of variables. Then the variables will tell us automatically whether it is possible, and if it's possible, then how many are required. And if it's not possible, then the variables will also tell you that it is not possible. Okay, so that even without thinking, you can say it. So in the sense that if it's complicated, then maybe thinking is not enough. You have to use some maths. So how do we do it? Okay, I mean, if it was, so suppose for the moment it was possible, okay, and let's say that if x northeast moves were needed, so we know that it is not possible, but let us say in general we were doing this. Okay. Then if x northeast moves were needed, and if y, you will see how similar this is to the previous questions. So this would be southeast. Now, can you give me some relations? So just writing it in full. Then what could you say about x? I mean, what constraints would hold between x and y? Anyone? Remember, you're trying to reach 8, let's say 8 comma 9, 7 comma 9. That's I can say in general m comma n also you can think, but just to keep it. If we are in abstract just saying x northeast moves were used, and let's say y southeast moves were used or were needed, depending on how you approach it, then what could you say? Or then where would you reach if x northeast moves were used and y southeast moves were? Then what would be the x coordinate of the place where you reach? Or if this was needed, then what can we say relation between x and y? Yeah. The other way to put it is if x and y respectively northeast and southeast moves used, then where would you reach? Now this you must be able to answer. Absolutely, right, exactly, yeah. Then x plus y would be the x coordinate of where you reach, and x minus y would be the y coordinate of where you reach. So this is where you will reach. You see, this is very clear, right? Because every time you make a northeast moves, you contribute to the x coordinate. Now you can write that. Every time you make a southeast move, you contribute to the x coordinate, right? And the difference is where you end up in the height, right? So every time you make a northeast move, you go up one vector, and every time you make a southeast move, you come down. So the difference is where you will, the net effect, the net rise would be that, right? I suppose that is very clear. Okay. So now you can look at this and you can say something very, so first of all, let's just check for this case. So in our case, so just writing it here, in our case, so see, when you introduce these variables, you must relate them. Okay, it's very simple idea. This introducing variables is very useful because it reduces the load on what we need to think. It gives some of that load to algebra itself. Okay, so we can focus on the other things. And that's really what we do in math, right? We use the language, and so that does the thinking for us, and we think of the non-mathematical thing to set it up. So in our case, what do we have? So in our case, we would have x plus y. If x moves, northeast moves were needed, and y southeast moves were needed, then x plus y should be 8. Okay, and x minus y should be 9. Now, if you just look at this, it's obviously not possible. And obviously x and y are not negative, right? So this is obviously not possible. You can just look and say, or you can try to solve and you will see, you'll get some negative answer. So is it clear that this algebra helps you to give this answer? Yeah. Okay. Okay. So you see, this is the thing. You introduce, this is like using algebraic reasoning. Okay. This is just a different flavor. Now, but the algebra actually can tell you a lot more. Now, these things you could say by combinatorics also, just like was said that Pragya said, I think, yeah, that if you just move northeast, 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 then at best you will, the best height that you can reach is 8. So obviously you cannot reach 9. That's a very straightforward way to say. That's perfect, right? But let me ask you another thing, and let's see how you can say this algebraically. Also, you can say combinatorially. Also, you can say it's your preference. Okay, there are several ways to approach things. Let's say somewhere distant, you want to reach 98, 100, and no, that would again not be possible. But 98, let's say 98, 7. And no, this is already. Let's say 98, 71. Yeah. Now tell me how many paths are there, and or if there are no paths, then say why. You can use anything to say. That is not the problem, but your reasoning should be correct and answer should be correct. So now we want to reach to this place. So the question is, okay, so yeah, so what are you using, the algebra or? Right. Okay, so that's perfect. Okay, yeah, this is obviously not possible. Again, if you solve, you can see. So basically both, and you already see it, both would either need to be even or both coordinates need to be odd. Right? So wherever you reach, yeah, both of them should have the same parity. Okay, so simply put in, and there's nothing to remember here. It's just very obvious. You just set up these things and you would know the answer. Okay, so so the parity of both the coordinates has to be the parity of both the coordinates has to be same. Okay, if you're reaching somewhere, the parity of both the coordinates has to be same. Either both has to be even or both have to be odd. By this rule, I'm talking about starting from the origin and following this rule. Okay. So now you also know how to solve this problem, right? If I give you 98, 70, then use this. Now I'll not complete this part. This is absolutely simple. Use this equation, like 70, solve for the x and the y, then you would know how many northeast and how many southeast, and then you would know how to do it. Okay. Okay. So I suppose that is good. Yes. So Ishana has joined a little late. Okay, no problem. The lecture is being recorded, so I will, and in the end, you can do it. So okay, let's just 1 minute. Yeah. So let me then ask. So let's ask a new question. Okay, no problem. If you have missed it, no problem. I'm asking a new question, maybe, which will not be so new for the people who are already were there, but still it's a new question. Let's say that you want to use diagonal moves just like yesterday. So this is okay. So here is the question. So we're using diagonal moves and we want to reach, let's say, to a place. So this is slightly abstract. Okay, so try to understand it. You can take a number and try, but you want to reach m comma n. Okay, where m is odd and n is even. Yeah. So now you can take an example. You can put an example there. But I'm just doing this in general for a certain reason. M is odd and N is even. You want to start from the origin. So the question is as before, you want to start from the origin. You want to use this diagonal moves and you want to reach M comma N where M is odd and N is even. Now, you want to show that there is no such path. There is no such path. Okay, so to put it completely from 0 comma 0 to M comma N. Okay, but I want all of us, some of us have already done it algebraically. I want us to think about this just with basic reasoning. Can you explain without using algebra? Yes, yeah. Why you cannot reach M comma N, the point M comma N, where M is an odd number, but N is an even number. Because it has this to be able to explain it algebra combinatorially or just by basic reasoning, I should say, has a lot of significance in other problems later on. So we want to show there is no path from here to, you can put some numbers, you can put maybe 100 comma 73 or something. So once again, starting from 0 comma 0, we want to show you cannot reach, basically want to show you cannot reach 100 comma 73 by using the diagonal moves. Okay, I mean, in fact, it's also true that if you use all 4 diagonal moves, even if you start using this and this and all 4, okay, so you can come back like this, you can do this, you can do all 4, still you cannot reach actually, but we can keep it simple and just use the 2 moves that we had, as you can see examples on the board, northeast and southeast. I mean, one can put this like a graph reachability question. So this is actually a graph, right? Where the vertices are these points and the edges are these things, these northeast and all. Just draw all possible northeast and southeast edges. Those will be your edges in the graph, and the points are your vertices. And you want to show that in that graph, 0 comma 0 and 100 comma 73 are not connected. That can be put in a very interesting way, okay? But I'll say that sometime later in graph theory class. But right now it's a very simple problem. You cannot reach from 0 comma 0 to 100 comma 73. So anyone, or if you want, you can. So yesterday we already did something like this, right? Where we said that you cannot reach 9 comma 0. That was an example. So it's not like we have not done this question. We have done small case like 9 comma 0, you see, even and odd, like similar. It is not like till 8 comma 0, but there was something more you have to think. Yeah. because there is no restriction on the number of moves that you can make in some sense. No, that's not correct. That's not correct. You can reach 15 comma 15. Just keep going. Yeah. I mean, so just use the two directions, northeast and southeast. Yeah, that's an easier question. If you use any direction, then that's a harder question. There are two more directions, but if we just keep these two for a minute, then ask the question. Just like yesterday. Yeah. So algebraically, yeah. Yes. So, so then how do you give a reasoning? Yeah, one has to be, yeah, that's right. So algebraic reason we already gave that if you need x this kind of moves and y this kind of moves and x plus y should be, that we already saw, and x minus y should be 73, and then from there you can say, but I don't want to use this for a minute for now. Okay. Yeah, we want to just reason it in a very different, slightly different way, which is by combinatorics. You see, so basically I'm saying that if the parity of, if these two parity are different, right, of m and n, the parity is different. One is odd and the other is even. But you see, you're starting, this is the matter. You're starting from a place where the parity of both things is the same. 0, 0, both even. Okay, this is the main thing here. So we want to analyze the process step by step. Starting from 0, 0, which means both parity same. Now that can be said in a lot of different ways, but both parity same. Okay, so if you are at a point, if you are at, just think about it, if you are at any point x comma y where both the parity same, if x and y are both even or both odd, okay, which basically means 2 divides x minus y. You can put it anyways, okay. If x and y both have same parity, then if you use any of these two moves, if you go here, then what is the parity of x and y? Same. It remains the same. Agreed? Yeah. If you move southeast, parity remains the same. The numbers change, but what is not changing is what we are interested in. Right? The parity remains the same. Okay, so if you are anywhere where the parity of x and y is same, then you take a step. When you take a step, you reach to some place, but those two places, possible places, will again have the same parity. Now from there, you again take a step. Where will you reach? You can only reach to place where your parity is same. Now, does anyone see how to finish this? See, the parity is not changing. If you are at a place where the parity of both is same, then the parity, wherever you reach in how many steps, whatever, parity of both the coordinates will remain the same. And also, if parity of x and y is different, then it will remain different. Okay, so now to put it in this context completely, you're starting with somewhere where the parity of both is same. Now think about all the places you can reach. You can reach 1, 1, or you can reach 1, minus 1. Both parity is same, both are odd. Again, you think where all you can reach. Again, the parity of this, both the parities of this will be same. For this also, both the parities will be same, and similarly for this. So the wherever you reach, the parity has to be the same of both the coordinates, because in the beginning it was the same. Okay. So at any step, parity of the two coordinates remains same. That's all. That's all we need to say. This is an example of what is called invariance principle. Right now, this is another topic that you would see, in any general combinatorics book. Okay, you find it in everywhere. In Brualdi also, any book you see. Yeah, this is an argument like in invariance. What does not change? So to show something is not possible after certain number of after a big number of steps, like here we are not putting a restriction on how many steps. You want to show something is not possible. Okay, so that's why you have to find something that does not change. Okay, so you have to analyze what is the difference between this and this. Like you already know it's about the parity. That's what the question is centered around. And so that is not changing, and that you can already see if you take some small examples. Okay, has anybody not got it? Is there any question? Please ask. So some question comes up. Okay, so everybody has got this. Yeah, you have to show for X and Y, right? You have to say this in general, that wherever you reach, the parity of both of them will not change. To say that, right, you have to say this general thing, right? That if I am at a point where the parity, because after 100 steps, starting from 0, 0, after 100 steps, you can reach so many different places, right? 2 to the power 100, something like that places, right? Maybe. Okay. So you cannot write all the cases, but you have to say that wherever you reach, my parity of both the coordinates is same. And how will you show? You will say that if you are at some step, you are at a place where the parity has not, of both the thing is same, then from there you take a step, the parity of both will also remain the same. So it's not changing. Parity is not changing. So wherever you reach, the parity will not change. Okay. So it is not changing after first step, after 10 steps, after n steps. So after n steps, if the parity is still x comma y, if x comma y and the parity is same, then at the n plus 1th step also, the parity will not change and it will never change. That is the thing. Okay. So this is the thing. It's a very complicated process, but something simple is not changing. And that is allowing us to just show that it's not possible. Does everybody get it? Get this one? Okay. Obviously, you don't need this kind of reasoning for this question. You could have done it algebraically very simply. Right? That if x moves, if it was possible, and x moves, y moves, you can reason based on that. But this reasoning is very, very powerful, because it is like differentiating the process, breaking up the process into steps and saying that something fundamental is happening. Okay. Like it is not just that here it is somehow not happening. It's not a coincidence. It is never true that you cannot reach anywhere where m and n is different parity. Okay. So by the same reasoning, if I start with, let's say 1 comma 1 comma 6. Now starting from here, you can see wherever you reach from starting from 1 comma 6. If you start from 1 comma 6, then wherever you reach, the two coordinates will always have different parity. So then you will reach this. And that I have not shown, but for example, what I have shown is if 1 comma 6 is there, okay, if 1 comma 6 is there, then the parity of 1 and 6 is different. Now just see where all you can reach, at least in the first few steps, right? It's a very simple reasoning. You see, you will reach to 2 comma 7, different parity, or you will reach to 2 comma 5, different parities. And you see always the parity will be different wherever you reach. Same reasoning you can say that if I am at a place where parity is different, x and y parity is different, then again parity will remain different. So wherever I reach, a parity will be different. So then I cannot reach, for example, 100 comma 100, something like that. I cannot reach this place from 1 comma 6 because this has same parity. Okay. Is it okay with everyone? Okay. Okay. So this was the thing, and this is just touching upon this invariance kind of reasoning, which is a very, it's again a different thought. You know, it's a different idea that can just change everything. Okay. Yes. So now let me go to the problem that we were doing that I had given yesterday towards the end of the class, and let's do that. Okay. So yeah, so yesterday's problem. So where we had 3 moves. Okay. Yesterday's problem. Okay. So we had 3 moves. What were the moves? Either you take northeast, or you take southeast, or you take 2 east. Okay. Yeah. And then just to keep it simple, we asked, yeah, just to keep it simple, we had asked, for example, how many ways are there using this rule to reach from 0 comma 0, let's say 10 comma 0, right, with this moves. So has anybody made any progress in this? Maybe I can draw some lines, right? That will help. Yeah. Okay. And then draw some lines. So this time again, we have 3 moves, and we had done a similar question like this. Sorry, pressing the shift button too often. Yeah. Yeah. Okay. So let's think about this. The So no one has made any progress in this. Okay. I mean, so now I will not draw the dots because the grid I've drawn. Oh, wow. 1 minute. I'll keep this picture. Yes. In the Yes, but also if you remember, we had done a question where we wanted to reach, let's say, 5 comma 5, and the moves were, so I think all of us will recall this, where the moves were you move like this, this, or this. You remember? To reach? Okay, okay. So to reach 1 comma 0. Okay, that makes sense. Yeah. Yeah, but you do see that there was this third prop that we were doing. Okay. Yeah. So we come to that, right? So to reach, I will not say A1, I will say A of 1 comma 0 because this is not a one-dimensional question. Okay. No, so there are 0 ways. You can you reach 1 comma 0? No, right? Because you cannot take one east move. Now, if I make that one east move, then the problem becomes very, very difficult. That's why I'm not doing that. Okay. If you make 2 east moves, yeah, it's 0, right? Yeah. So it is a 0. Okay. And then what? So yeah, this is 0. And similarly, if I make 2 comma 0, then a 2 comma 0 is how much? 3. You can also go down, remember, okay? You symmetrically, you can also go down. So you can see there are 3 ways, okay? You can either go like this, or you can go like this, or you can just go flat, okay? So there are 3 ways. Okay. And it is again very similar. So if I ask, lead you on, if you take this is 1 and this is 1 minute, sorry, so this is 1 comma minus 1, this is also 1. You can see something is happening, something similar we have done, right? And then we can ask for other points also. But it's a little hectic in this way, in this particular version. Well, yeah, 5 comma 5 is obviously not here. So you will, so the claim is that you can continue like this. Okay. If you just continue this pattern in this way, you will see that it is very similar to the previous, the one of the problems we had done. For example, you will see this pattern. Suppose you want to reach this point, a of 7 comma 2. Okay, now you see this is very simple. A of 7 comma 2, how can you reach? Just ask yourself, how can I reach here? What is the second last step? I will either it will either be coming from here, right? Or it will be coming straight from here, or it will coming from here, right? So if I know the number of ways to reach here, or here, or here, I can add them, and that will be the answer, right? Just like the previous question. Sorry, I mean the first question rather we did yesterday, right? What we said, the Dillanoy paths. This is in fact it's same question, okay, in some sense, but slightly different in the sense of exact numbers. So is it clear that this will be again a of 7 comma 2? So basically, just if I want to reach 7 comma 2, then I would have to pass through the and so I'll just need to add the number of ways, right? So either it will be from 6 comma 1 or from 5 comma 2 or from 5 comma 3. Is it clear to all of us that this is exactly what it is, right? You have to reach here, here, or here, and from there are only one way to go to 7 comma 2 from each of them, right? And in this way you can count. In this way you can move and you can count. You can reach 10 comma 10 after some time, right? This will be your zone. Obviously you will not go outside this. If you go outside this, you will never reach 10. Inside this, you have to fill up all the points one by one, and also below. That is symmetric, so not a problem. Is this okay with everyone? This is just very similar. Just start filling this grid up. We'll start filling all these one by one. Within a few minutes, you will reach here. But you cannot just stay on this one dimension and do. No, that will not work. You will need the things above also. Because here you can come from here, but here you could have come from here, and so you will need all of them. Okay, so you have to fill it up in a sensible way, then you can do it. So is the road clear? But you have to still do the calculations. It will be not difficult. Yes, but that will be symmetric, right? The answer will be the same. uh, no, but you see, there will be some paths that, no, so that's probably what I'm saying is not completely correct. So the thing is that I will not say double, I will not take that the thing, but the point is that suppose you want to reach this point, you should fill everything. Okay, so fill everything. Okay, why I'm saying fill everything, because you cannot just fill the top numbers. See, you basically cannot just fill the top numbers, because when you are at this point, then you have to ask yourself about this. You have to ask this, and you have to ask this. So you will need to know what is the answer for this. It is the same as this, right? But you will still need to write the answer for this point. This and below, you will need to know these three. So you will, yeah, you will need to know. So simply doubling is not, because there are some paths which cross, right? There will be some paths which may go like this, it goes like this, and it goes down, and it goes something else, something it does, right? It goes crazy then. So you have to count everything. So because the paths are not just completely on top or completely on the bottom. In fact, those paths are incredibly difficult to count. If I put the condition that the paths have to always be above, that is a difficult question. It's not half, you can think. Yeah. We will be thinking about that later. That's a difficult problem. So it is just the very similar. You can see it's very similar to the previous things, a recurrence problem. But I want to do this in a slightly more interesting way, which brings out a new idea of further use of symmetry, and rather of what is known as translation. So I will do some sort of I should not say translation, sorry, I should say transformation. Okay, so a transformation technique. So what is a transformation technique here? Transformation means that, see, you can already feel that this problem is very similar to the, or to which problem? To this problem, northeast and northeast. We have done this problem, right? Where you have to reach 5, 5 by using these kind of moves. You see? Yeah, we have done this question. Now you can see that this is very, very similar. It is just a very similar recurrence term, but it just seems a little rotated, right? So that's what I want to show, that so basically what we feel should be true is true, but to show that we have to formally say something. Okay, so we want to use a transformation. Okay, so let's do that patiently. So what I'm saying is, the idea is, I want to convert this problem directly into this problem. Okay, you will see how. So we'll just remove these things first. And this, okay. So this converting one problem into a different problem, which can be easily solved. So no, we'll end up in a different point. Yeah. So I will convert this problem to this problem, but the point will not remain 10, 0. It will become 5, 5 actually. If you just think also, you see, if you rotate, right, it feels like that. See? So yeah, the exact numbers will change, but the problem will get transformed. And then you can just do it there, which is a more convenient, familiar place. And this kind of transformation is it's actually game changing for some problems. For this problem, it is not, because you can do this problem by lying down, by lying like this, just like this only. You don't have to rotate. Uh, but already it's a little inconvenient. This version, it would have been better if it was northeast and northeast rather than this northeast southeast thing, right? So that's what I want to, that was a more convenient version, so we want to just convert to that. So let's see. Okay, so first I'll say take a path. So step one, okay, I'll say take a path in problem one So this is problem 1. Problem that we have. Let's take a path in that. Let's draw one simple path. I'll be drawing a path that no, I will not be drawing a path that just stays above. Otherwise, I don't want to give the impression. Otherwise, you will not see the difference. So let's actually draw this line actually in bold. And so I'll just go a little bit down sometimes. So, and once you see this technique here, then you can later on apply it in all kinds of places where you have to do this transformation. So let's take a path. Okay, let's take a green color and let's take a path. So let's say the path, I'll also use the arrows, moves like this. So moves like this, moves down, moves down, moves up, moves down, moves down. Okay, this is fine. This is just a path. Okay. Now you know what is the goal. The goal is to convert this path, or from this path, you want to make a path that is of the second nature. Okay. So make an ordinary, or not, let's not use all that. Make a path which uses north, east, and northeast moves. Okay. Okay. I'm sorry. I didn't. I should have used some 2 of the east moves, right? If I don't do that, then the purpose is defeated. I mean, then also you can see that this transforms, but let's just see it in one go because we have already done it, right? So, yeah. So what to do? Let me make some more changes. So I'll make a change here also. So the point is that everything. Okay. Now how do you make that conversion? It's a very natural thing to do. So the idea is that you want to somehow take this path and rotate it by 45 degrees. So this one, though that's not theoretically correct. You cannot just say rotate because something goes wrong. You see, you want to look at this one and you want to make this horizontal, right? You want to look at this one and you want to make this vertical, and this one will become diagonal. So this one will again become vertical, and this one will become diagonal. Okay, but it doesn't just happen if you do a plane rotation, because I mean, this diagonal is obviously bigger in length than this. So it will not, the grid will get stretched and so on, right? Which will not change the combinatorics, it will not change the answer, but we want to do it. The idea is this, we want to just say it in a different way so that we don't have to say a lot of things. Okay. So what is it that we'll say? So I'll say that every time there is a, so let us just see it like this. So let's write this path in the language. So this is like, so this particular path that we have encoded, it's southeast, it's northeast, and then there is another northeast, then there is 2 east. Now 2 east is different. 2 east, maybe I'll use say E2, right? That's better. Then I'll use southeast, then I'll use northeast, southeast, and then E2. This is the path, right? So what I'm saying is, basically what we wanted to say using rotation, we will say it in a different way. That's all. Okay. So what I'll say is that every time you see a southeast move, do an east move. So I will create a different path, right? That's what we want to do. We want to convert it to a second problem. So every time you see a southeast move, do an east move. Every time you do a northeast move, do a north. Okay, every time you do a northeast move, do a north move. Okay, every time you do an east E2 move, just do one diagonal move, one diagonal. Okay, and then continue like this. So every time southeast, you get a east move. Every time you're northeast, you get a north move. You get an east move, and you get a diagonal move. Okay, let's just apply and see where this path ends. Okay, you can also guess where this will end. But let us apply it and see. The guess obviously that it should end at 5,5, right? but we can see. Southeast goes to east, so I'll just construct the path. Let's do it in blue only. So we have this east, then we have north, then we have north, then we have one diagonal. Okay, and then we have again have east, north, east, and one diagonal. You see, you end up at 5,5. Right? So I took a path in the first problem. I did this conversion and I went to this path in the second problem. And you can also go back and forth. Does everybody see that? Right? You can just go reverse also. Just do the reverse. Okay. So I'm taking a path in the first problem, matching it to a path in the second problem, which is just a rotation in some loose sense. Okay. And then I'm taking a path in the second problem, and also you can just reverse the process. When you see an east, you do a southeast and all that. Just reverse it. Okay. Now what you do have to show is that every path from 10, 0 in the first category gets converted to a path in 5, gets converted to a path that ends at 5, 5. You have to show that, right? You have to show that if, so this is my P2. Okay. If the path, no, but it is not, 45 degrees. So it is, if you just do 45 degrees, then you see this green path will actually not become this. It will become slightly little extra because it's bigger in length, right? It's a diagonal. If you just rotate. Right. So that's where, but you can feel that the answer will not change. Like this will become a rectangular grid or something, but the answer will not change. Right. Because it's a counting question. It's not about whether it's a rectangular or whether this square is bigger than this square. That doesn't, all those things don't matter. This is just a graph, it's just points and lines. It's a combinatorics problem, right? But still, to be safe, you don't want to say all that big philosophy things, right? Simply, I can just say, just whenever you see a path like this, you do this conversion. Like this is what we wanted the rotation to do. The rotation is not doing it, so I'll do it by combinatorics. Okay. Right? This is exactly what you want the rotation to do. But then you're seeing that the rotation, it's a little bit, the geometry is interfering in the problem. So I'll leave that. I'll use the inspiration from geometry, but I will use the combinatorics to do the transformation. And now this is a non-controversial way to do the problem. Like I don't have to write much. I'll just say reverse and so on. But you do have to show that if a path in, and this is also obviously, you obviously have to show this, if a path in problem 1, ends at 10, 0, then the new path, then P2 ends at 5, 5. That is not difficult. Okay, that is not difficult to show. Just try to show this, but you do have to show this. It looks obvious. It should have happened. That's why we did these moves, but you have to still show, right? That if any path ends at 10, 0, then the converted path will end at 5, 5. It is not completely trivial because you have 3 kinds of moves. So you have to do, X, you have to say X southeast moves, and I'm using Y northeast moves, and I'm using Z number of E2 moves. You have to find a relation between these things. And then you have to show that in this, that adds up and so on. Okay. But just try this. Okay. But you see, you have to show something. Is it clear to everyone? Right? That every time you take a path here and I'm converting, it should go there. Now it depends on the level of rigor. For some maybe exams, they will not cut so much marks if you don't actually show it. It depends, but you should show it. Otherwise, how is it done? Okay. So then basically, but it will end. You can understand, right? Any path like this will end. I will do this rigorously the next day, certainly. Okay. but you try it yourself. Take some more examples and see it will happen. Okay. Yeah. So the second, so this is basically, so this problem where it ends at 10 comma 0, this is the same as a problem that ends at 5 comma 5 with this, and this is something that we have already done. So you see, it's the same. You see, so the number of, so the answer for the first problem will be same this, right? Because any path here is matched with a path here in the second problem, right? So number of paths in the first problem will be same as number of paths in the second problem, because there is a, no, I can take a path in the first problem and convert it to a path in the second problem. I can also come back directly. There's a direct matching. You can just say a rotation also to put it in one word. Okay, this is the idea that we will continue with, of taking this path and converting it into a new kind of path. Okay, by this naming. This naming was obvious. Some namings may not be obvious sometimes. So sometimes it will be tricky. Okay. So any questions? Yeah. Yes. Why is it ending at 5 comma 5? Because you can see I showed in one example that it ended at 5 comma 5. You reason. Okay. Yeah. Yes. Obviously. Yeah. That's exactly correct. There is. Does anybody see why it? Can anybody? So let me just say a few words here. Let's see. Or does anybody know why it is ending at 5 comma 5? Because it's not just a rotation, it's a rotation and a kind of contraction, right? It's a rotation and a kind of contraction also. But you're right in asking. I mean, it's in the sense that it is not completely obvious, maybe, if it's seen for the first time, that it will end at 5.5. But you can understand, I mean, the total weight is getting distributed. The total weight is still 10. Okay. But yeah, that is what is happening. The total number of steps. Yeah, but that's not a very good reason. Yeah. So can I explain? Yeah. Hmm. Yes. And also this double one, I am making it into only one diagonal. Okay, so that's a rough explanation. But I'm just thinking if there's some other explanation that we can give without proving it. Obviously, one can prove it also, which we'll do next time properly. But yeah. So basically, it is like, see, every time you apply a force, every time you are applying it's a force of 1 comma 1, this is getting converted to 1 comma 0, right? Every time you're kicking, you're from here, you're starting and it's a Brownian motion or something. It's the particle is just getting moved randomly, getting kicked to, or no, this is the wrong example. This is 1 comma minus 1. So every time you are doing this 1 comma minus 1 force in this world, that is getting transformed into uh, 1 comma 0, right? 1 comma minus 1 is getting transformed. So the 1 comma minus 1 force is this direction force is getting transformed to this. Similarly, when you do a 1 comma 1 force, that is getting transformed to 0 comma 1. Similarly, when you're doing this 2 comma 0 force, which is the 2e move, e2 move, that is getting transformed to 1 comma 1. This is what we are doing, right? And you see, this also follows. This third equation, this third thing also follows from the first two. If you add the first two, right? This 1 plus 1 is 2 and 1 minus 1 is 0. Then this also adds to 1 comma 1. You see, the 1 adds and the 0 1. Okay, so it's consistent. It's a consistent thing. Okay, if 1 comma minus 1 gets transformed to 1 comma 0, 1 comma 1 gets transformed to 0 comma 1, then 2 comma 0 will get transformed to 1 comma 1. But this is by addition. This is how I like kind of cooked up the question quickly. I didn't have the question with me. I just cooked it up because of this. But the question is, can we use this to explain? That still remains, right? So No, the angle, because it's not really a rotation, there is a problem. Yeah, the angle might tell you that it should be x comma x, but why 5? That is a question. Uh-huh. No, but the angle got reduced where this distance, this is about distance. The distance has also got reduced, right? The distance has also got reduced, right? So so all this is intuitively, so we have explained, because everything is here shortening. But let's just take a minute, I think. So if you're doing otherwise we can just prove it using the variables and so on. 1 minute. Some of the coordinates. Yes, right. That's the reasoning. See, so see, every time you're making any of these three moves, right? The no, that's not correct. The effect, I was going to say, the effect of this, but the effect of this is just one, right? So 1 minute. 1 minute. So 1 minute. Yeah, but if I say more now, it will just become the proof itself. That is a problem. Yeah, so I can say like this, but it will become really uh, too much details. Not. That is actually finished. Let's actually do the proof. Okay, so that I think, because it's not good to keep this hanging. Okay, let's actually do the proof. So see, no, I should not remove that, right? I should keep this. I can remove this. Yeah. So you see, okay, let's say that, let me write this. Yeah. So let's say that in the first one, you're making x northeast moves, you're making y southeast moves, and you're making, yeah, I just take 5 more minutes, that's all, not more, because it's a, I think school is not open, but still we should sleep on time. So let's say you're making z e2 moves. Let's say I'm making these moves. Okay, so if you're making these moves, and where will you reach? Okay, and so I mean, so you're reaching 10 comma 0, so what will be the relation between these numbers? That's the question, right? So x northeast moves, y southeast moves mean that this will be the effect on the x coordinate, right? But if I make z e2 moves, that has 2z effect on the x coordinate. Please check that, right? That's obvious, right? Every time you make a z move, it has net 2 effect on the x coordinate. Yeah, and similarly, x should be equal to y, because x minus y should be 0, because the net effect on the height is 0, and the e2 move doesn't affect the height at all. It's just about the northeast and southeast. So this is the situation. Okay, so if you use these two equations, you get, what do you get? You get x plus z is equal to 10. That's what you get, right? You get x plus z is equal to 10, and yeah, and x equal to y. Does everybody agree? So you cannot actually say what is x, y, and z, unfortunately. In this problem, you cannot exactly say, and that's why the problem is difficult, right? I mean, that's why this problem doesn't have a formula. One has to do it by this using small cases and so on, right? But this is what we know. We know that you have to make some x moves, some y moves, but they'll be equal, okay? And some z moves, and total x and z. No, so the total should be 5, right? Sorry, this should be 5. Does everybody agree? Please just take a minute and see if this is okay. I mean, it's not okay, please ask me. Yes, x equal to y is because we want to end at 0 in the height. This is a partial answer. Okay. So x is the number of northeast moves, right? So every time you make a northeast move, the contribution to the height is 1. And every time you make a southeast move, the contribution to the height is -1, right? So if you're making x times you're going up and y times you're coming down, which is northeast and southeast, that should be equal, right? Because you want to eventually land at 0 altitude, right? That's yeah. Okay. So then we have this. Now you see, now what does this mean for us? Okay. What does it translate to in the second path? So maybe we can just create some space here. What does it translate to in the second part? Well, it translates to this. It translates to x x north moves, right? Y east moves, E moves, right? And Z D moves. That's by very definition, right? Every time you make a southeast move, that becomes an east move. So Y basically is E, right? Number of times you make southeast moves is the number of times you make E moves. So okay, that's is it okay? This is what it translates to for P2. In P2, this is what it translates to. Okay. So now x is equal to y and x plus z is equal to 5. Now you ask yourself where you will reach if you make this like this kind of moves. So x is equal to y. So you're making equal number of north moves and equal number of east moves, right? So we want to show that you will reach 5,5, right? So you're making equal number of north moves, equal number of, so you're making x north moves, right? So you're making x times you're going up, right? And the rest of the times means 5 minus z times you're going diagonally up. You're using the diagonal move, which means you're also going up. So totally you're going 5 times up, you're going up. So you'll reach 5 height. Or I said it wrong. I should say y, right? Yeah. So let me say it again. But before that, let's just take another minute. Just, I think, let's come back. Is it clear how this transforms to the P2? In P1, we have this many x moves, y moves, they are equal, x plus z is 5. Now that transforms to P2 in this way. That means x north moves for the P2 path, right? Y east moves and so on. Okay. Now you try to convince yourself that this means exactly, oh God, yeah, yeah. This moves exactly, this means exactly that you will reach 5,5. And that's very clear because if you're making x north moves, okay, x is north here. That's why it's confusion, right? Yeah. If you're making x north moves, so this is north and this is diagonal, right? But that's also north, right? Which means that totally you're going north 5 times. Yeah, that's what this equation means. This means that totally you're going north 5 times. The x times you're going north, and then z means you're going north also. Meaning the effect of north is still 1, right? For every z, for every diagonal move. And so you're going north 5 times. Similarly, you're going east also 5 times. Simple, right? Because if you're going, so this is also means, yeah. X coordinate. Exactly. And that total is 5. And so you will, yeah, okay. So there is some freedom in this, in the sense that the x and the z are not known, and it cannot be known because you can see you can use different numbers. That's why this problem is difficult. But total you will reach 5,5. There is no problem with that because x plus z is 5, and x, every time you take an x, you're going 1 step north. Every time you take a z, you're also going 1 step north and 1 step east. But we don't care about east for a second. You're going 1 step north. Z is doing the job of both of them. Okay, that's why the 2Z I had to. That's why I had to put 2 east here. Okay. Anyways, this is the thing, and this is the reasoning. It's not that difficult. It's just some bookkeeping. You're just doing some arranging things in a good way so that we can just look and argue. Okay. So yeah, let's stop here. It's okay. We went a little slow today, but I think it's important to understand everything. And I will share the recording. Someone joined late. So I think Ishana joined late. You can review it, watch it. And I'm not giving any problems today. We'll do it next time. Okay, I have some problems in mind, but let's take a break for a few days, study some other things, and we'll start soon. We'll resume. Also, obviously, there are questions. I told you to think about some variations.